So the free body diagram, which is a sketch where you show the object and all the forces acting with it.
Okay.
So there is the object, and it is moving right towards a detector. Like,
yeah.
let's say that the detector is this one, like this, D.
Yeah.
And this is the cart. And there is a fan pushing it in the opposite direction. So, I don't know, how do we draw it? Like this. This is the track. Let's give it a plus sign here, so X.
It's positive direction.
Yeah. Yes. Okay, so shall you draw something to start with?
Like,
well,
okay, so we do have, like, partially, we have the diagram, kind of.
We do.
So, yeah, of how it is. So, 50, flat track. Initial velocity towards... Oh, why is it like that?
Just need to get used to it.
Sensitive to, like, how hard I press.
It does.
Oh, and now it's not letting me write. Yeah. Wait, no, it's just like that. Okay, sorry.
That's
that
fine.
Was so off.
So what is acting on the cart?
Okay, first the initial, like, applied force. Right?
Well, the text doesn't say that it is applying a force. It is given an initial velocity. So please do be careful when using words, because forces and velocity, by the way, do not sum up. So if you draw, if you draw a body and put F like this and V like that, they don't sum up.
Yeah.
Okay, so what forces act on the cart?
Okay, well, gravity, first of all, and then normal force.
Gravity is always there, which is a good thing. Oh, shall I just quickly jump in? Straightforward. mg.
Oh, okay.
Okay, I don't know how you used to call it. I would call it n. Just doesn't matter.
Yeah, that's what I did.
Okay, so now, do we put the velocity on this graph?
No, because this is just forces. So now it'd be force of friction.
Not only. There is another law of
Air
Newton.
Resistance?
There is another law of Newton telling you that whether it moves at constant velocity or it stays put, there is no difference.
Yeah.
Okay. So what else? What else?
So friction.
Well, is it moving?
Yeah.
Then we suppose that it is moving towards the right, so towards the detector. What is acting as forces opposite? Exactly. Which forces are opposite?
Normal force and force of gravity, and then force of friction versus force of...
Well, there is the fan. There is the fan, which you haven't mentioned. So the fan pushes it the other direction. So this is the fan.
Yeah.
Okay. What else?
Wait. Oh, yeah. And then the force of friction is actually this way. Is it? No. No, it's this way. Right?
Well, let's reason. why is it? Where I mean, let's step one.
Wait,
one
how did you get your line to be so straight?
Because I am a professor using this thing for already 10 years, but you can anyway use the line instrument, which is L.
Okay.
Okay, let's step into theory. What is kinetic? Okay, what is friction? What is friction? Let's say, and then we will inquire what types of friction do you know.
We don't know anything about.
Oh, you do. Oh, you do. Just grab your hand and start waving it throughout like this.
That's like friction, like air.
Okay. Now, what do you have on your table? Do you have anything rubber, anything heavy, something like that?
Not really.
Okay. Well, whatever object you have, just slightly push it with the tip of your finger. Gently push it.
Yeah.
Okay. Is it moving? No. No. If you
It's
push
being
it,
pushed, like,
if you push it gently, like a princess shall do, it doesn't move. But hey, second Newton's law, what is saying? That if you apply force to an object, this object,
the force is acting on you.
that's the third one. That's the third one. Okay.
Okay. Acceleration is net force divided by mass.
Exactly. So if something is receiving a force, it must accelerate. If it doesn't accelerate,
there's no net force.
There is another force countering. You are sure that you are pushing, right? You are pushing,
yeah.
But it doesn't move. So what does it mean? That there is something else pushing the other way around, like this.
Yeah.
Good. And this is the way to detect and understand that there is something called static friction. Static friction. You can take down a note, that would be appreciated. Oh, and as well, I talked with I guess he's your dad, or anyway, Ivan. As a part of the homeworks, I would really gladly have a look at the notes that you put in your mind. So after our sessions, please picture and send, and I will correct them if needed. So,
like the ones that, because I can't I have the problem open and I have your, what's it called,
I do.
Your whiteboard open.
Mm-hmm.
But usually if I take notes in a separate app.
Okay. Well.
So I'm not going to be taking notes on this app right now.
Okay. We'll sort it out later. I always encourage pupils having the old-fashioned paper and pen ready. But okay, doesn't matter. So if you push something which is standing, it doesn't move. Hence, you apply more force. What is keeping it fixed is the so-called static friction force. The static friction force has a neat formula that says, well, the static friction force depends on what? On the weight of the object, which means the normal reaction of the plane, times some kind of a coefficient, like this, where mu s is a Greek letter with predix s, like static. Okay, it's this, look, it's the normal force times the static friction coefficient. And this one depends on the surface. Depends on surface. Got it?
Yes.
Good. Once you overcome the barrier given by the static friction, the thing starts moving, right?
Yeah.
And if you stop pushing, what does it do? Does it go on as the first Newton law says, or?
No, it stops due to friction.
Due to dynamic friction. So, yes, I can write it if you wish.
No, it's okay, I'm writing.
So dynamic friction is what slows you down until you stop. It slows you down until you stop. Good. So, guess what the formula is? Dynamic friction force is as easy as the normal force of the plane, the normal reaction, times a coefficient, which again depends on the surfaces.
Oh yeah, because normal force... Wait, but don't normal force and force of gravity cancel each other out?
Yes, but we are looking at the normal force. Now, I can make a difficult example. Just imagine you standing on snow. You actually press down a little bit of snow, okay? You get deeper into the surface of snow, isn't it?
Yeah.
Your gravity was the same as the normal reaction, but the snow is not hard enough to keep you up, and so you sink a little bit.
Yeah.
But the friction counts on the normal force that the snow was applying to you, even if it is too low to keep you up. So in this case, we don't use the same value as the gravity force. But let's get back to the problem. So here, it is already moving. So what type of friction are we having a look at?
Since it's already moving, it would be dynamic friction.
Yes. So shall we draw this happy force, this happy friction force?
Is it the red?
No, that's the fan. Actually, let me write it. Fan.
Oh. Wait, so it would be...
What side is it moving? That's let's do it like this. Let's do it like this. So this is movement. So it is velocity and movement, x. But if movement is to the right, where is the friction force directed to?
Is it... Wait. Here.
Yes, of course. It is opposite to the movement. So you have two arrows on that side, which is the fan and the friction. Okay. This was the first part of the problem. Eventually, the kinetic energy of the cart runs out, it stops, and the only force pushing it is gonna be the fan. So the movement is gonna be, I would like you to talk me into it this time.
And then the movement would now be in the other direction. Like it would start moving from... Sorry, there's a parade in town.
I don't even know what town you are in. Is it Boston?
No, I'm in Exeter. It's a super tiny town. But there's like some kind of like marching band.
Well, in God we trust.
Hell yeah.
Oh yeah.
Okay. Hell yeah. Okay. So this is the diagram. This is still the fan. it's just fan.
Okay.
Like, so I remember.
Mm-hmm.
And now the object is like going like here, like that. And the object is going this way.
Right.
And this is the force of the fan.
Yes.
Right.
So what type of movement is it going to have in this case?
Dynamic?
Nah. Movement can be linear or linearly accelerated.
Linearly accelerating.
Yes, of course. Okay, so what about the friction in this case? Now this is the free body diagram for the second case when we are moving out of the detector.
Is that it? How you write like force of friction?
FF or just F, I don't know. But here let's write fan, and then you always need to have mg and n, isn't it? Yes, exactly. So this happily solves point A.
Yay! Okay. I think I understand what's going on.
Finally.
Okay.
Now, sketch a velocity versus time graph for the motion, please.
Okay, sorry, I just had to write that out. Okay.
That's it. You know, I was told you are a dragon in math. Well, we will make...
I don't know who said that, but that is not me.
I talked to your soul last night, and your soul told me that you are a dragon in math. You're gonna be 2 dragons in physics. Most likely,
down to an easier class.
Most likely because you're gonna like it.
Gonna like what?
Physics.
I'm gonna like physics. Yeah, I'm gonna move down to this easier class.
Let's check. Okay. Let's sketch the velocity versus time graph for the motion.
Okay.
Velocity versus time, yes, but I am saving some technical time instead of asking you what is the dependent variable, the independent variable, the control variable. All this is gonna be later. So, velocity versus time.
Yeah. Okay, so the velocity at first it is positive and then it becomes negative.
Mm-hmm.
And it's linearly becoming positive and linearly becoming negative, like with a linear acceleration. Right?
With constant acceleration. Constant acceleration, yes. Would you draw it?
Yes. So like...
Yes.
Like that.
Exactly. And you are asked to label the time when it comes to a stop.
I'm so bad at that.
Oh, come on.
I can't do that.
Come on.
Okay, so we have all of this.
Mm-hmm.
So I don't know like what friction. Like I don't know how to calculate friction.
Oh, you do, and we will talk about it in a moment. Label the moment when it comes to a stop. It is a trivial moment, but you gotta say this, like T stop. Something like this.
Okay. I thought it wanted us to find it, find exact time.
Okay, the car has a speed of 1 meter per second immediately after it is released. And it comes to a stop in 1.5 seconds. This is part of the text.
Okay, so this is 1 meters. 1. And it comes to a stop in 1.5. Perfect.
Good. So...
No, yeah, time.
Okay, if you wish, we can... No, that's second. That's the measurement unit. But we can happily do like this and look at this. This is very... very sexy. Look at this. We put seconds here and meters by seconds there. This is very... Okay, like this. Okay. So now, what is the acceleration of this thing in magnitude and direction?
Okay, so the acceleration.
What do we need to find acceleration?
Like how much it's slowing down.
So the time, and what else?
And the initial speed.
The initial velocity. And as well, eventually, we would need the mass and the force acting through it. But actually, of this thing, we have time, we have velocity, we have mass, and so we will be able to find force eventually, isn't it?
Yeah. We will.
Okay. So let's get the acceleration from these two.
Okay, so 1 divided by 1.5, right?
Okay. Sounds as a good idea.
That's like how much it's slowing down. Like
yes. It is. When it is going through towards the direction, the detector. And what else? There is something else missing here. Otherwise, the thing is wrong. So for the moment, it is wrong.
the force of the field?
No, it is way more subtle.
I don't know.
Oh, yes, you do. Is it slowing down? Then you gotta put a minus there.
Oh.
You know,
So it's negative 0.6.
6 something.
Yeah, 0.6 repeating.
You know, people would call it a tragedy if you wrote your name like this.
Why?
Because that's complete. Okay, let's make it another example. I can't say please call me. I can't say please call me, isn't it? That's an error. But people don't pay as much attention whether we mix up signs.
Okay.
So please, just a slight moral to pay attention to signs, whether positive or negative, do matter.
I understand.
Okay, so this is acceleration when?
This is the acceleration up until it comes to a stop.
Yes. So towards the detector.
So for 1.5 seconds, yes.
Towards the detector. What in the other case? Oh no, that's next one. That's next one. Point D, the distance traveled before stopping.
What do you mean? What about it? I don't get it.
Point D, point C is the acceleration. Point D is the distance traveled before stopping. Now, I tend to be. Go on.
It's just this.
Um,
That's how far it traveled until it came to a stop. Because this is a velocity versus time graph.
yes.
So it's the area of like under the line on the graph.
Exactly. Exactly. Well done. This is going to be helpful in the future.
Yeah, so it's 1.5.
Shall you look for a more formal way of doing it? X of t is the integral.
I don't know anything about integrals.
Yet.
Yeah.
Okay. Doesn't matter. Doesn't matter. No integral. Then it is BOT plus 1/2.
V like initial.
Yes, exactly.
Yeah.
T
VIT
squared.
equals to 1/2 AT squared. I know, yeah, I know that one. I know all 4 equations.
Okay.
Oh, wait, I actually do have a question. I'm really sorry for interrupting.
That's fine. That's fine. Go on.
Okay, I don't really, like, understand, like, this equation. Wait. I don't understand, like, what this corresponds to. Like, I understand how, like, displacement equation is the displacement equation. I understand, like, how the final velocity is the final velocity equation. Like, I understand those. I just don't understand this one.
Shall I give I was actually going to talk about this. You don't.
I know, but I know, but this is just for the future. Like, could you explain this today, please, maybe?
Well, I don't think we are going to have time, but whatever I was going to say is, being 4 equation, you only need 2 of them. Velocity, I mean, the final velocity is the initial velocity plus the acceleration. Exactly. And this one. That's it. All the rest can be derived by logics from these 2.
Yeah.
Okay. So what is, okay, so it is 0.75 meters, which is good.
Yeah.
What about the net force? The net force while slowing down. Second Newton's law.
Positive. And wait, negative because it's in the negative direction. Yeah.
You see, you're getting there. And how much is it?
0.5. Wait, 0.67.
That's the acceleration.
I don't know.
Oh, you do. Come on.
Oh, wait, acceleration equals to net force divided by mass. We don't know the mass of... No, we do.
A
It's
0.5
kilogram.
cart.
Okay, and now we can just into that. Acceleration is negative 0. Oh, sorry. Negative 0.67. No, wait. And then mass is 0.5. Now we just multiply net force equals to
0.33.
Oh, yeah, 0.33. You're so right.
Thank you.
Sorry.
I like preparing for the lessons. That's why I buzzed Ivan to send me tasks.
Okay.
Good.
I understand.
Now, what is the fan force given a friction of 0.1 Newton?
I don't understand newtons.
Oh, you do. You clearly do.
No. Is that 0.33 newtons?
Oh, yes. All forces are measured in Newton.
So it's 0.33 newtons.
Yes. As well as here the acceleration. Oh, okay. Here the distance covered shall be in meters. Thank goodness there is no yard here or miles or anything. And
no, we don't use those in physics.
Thank goodness. and the velocity should be in meters per second, and the acceleration shall be given in meters per second squared. So this is good. Now let's go for the fan force. Given a net friction, given a friction of 0.1 Newton. Now let's talk about Newton's second law.
It would be 0.33 plus 0.10. The force of the fan on the car is negative 0.43.
Actually,
newtons.
No. Because the friction...
No, because because it's moving. The friction and the fan are pushing it in the same direction.
Mm-hmm.
So it would be minus.
Yes. The problem is at the exam or at the test to have, the calm, the inner peace to have a look at what you are writing. Because when you have your drive, when you have your inspiration, saying, hey, no, I know that, but step back and look at what yourself is doing.
Yeah.
And so eventually the fan is 0.23 Newton.
So the acceleration of the car when it is... Okay, so if the force of friction, and the fact is that the force of friction is going to be, right now it's going to be working against the fan, right?
After it stops and goes back, yes.
Yeah, for G.
Exactly.
Okay.
Yes.
Yeah, that's what I thought. And now, wait, no, that's the wrong G. Sorry. Okay. And now, wait, no, that's F. Yeah, sorry.
That's fine.
Okay, and now, G. Just that way it's not confused for gravity.
Mm-hmm.
That's the question. G. Okay.
So quickly about the velocity times, the velocity versus time sketch. How is the slope of the first part compared to the slope of the second part?
Wait. So the net force.
Yes. Okay, are you done with that?
So it would just be 0.23.
Yes. Actually, hold on a second. You forgot friction. Friction is now working.
So it would be 0.33.
No, because the fan force is 0.23.
Oh, and then you subtract from that another 10.
Exactly.
Oh, yeah. This is the kind of little stuff that I get wrong a lot.
For the moment. Don't get used to it because soon it will be just gone.
Yes. Okay, so it's going to be 0.13.
Yes.
And let me go calculate that. Negative 0.26.
That's correct. Okay. Amazing, princess.
So that's acceleration.
Now, let's get back. Please.
Wait, I have a question.
Please go on.
Can I run to the restroom really quickly?
Please do that.
Okay. Sorry.
That's fine.
I will be right back. Very quick.
Mm-hmm. So, as a quick recap, if you are in your elevator with the scale, when you stand, you weight that much. Or when you are moving at constant velocity, that much. The moment in which your elevator starts pushing up, it is accelerating, going up. Hence, by the third Newton's law, you are going to push harder down. And so you're going to weight more. Good. On the flip side, when the elevator starts decelerating, namely accelerating the other way, you will read less on your scale because there is a reaction to the elevator acceleration in that way.
Yeah.
Okay. And all this is the so-called apparent weight.
Okay.
So that said, if a book, now I'm reading exercise 23, if a book is on your palm as you ride the elevator, you have an acceleration going up and then a constant velocity and then a deceleration, which means an acceleration downward.
Yeah.
You may want to draw the free body diagrams in these three cases. And then...
So should I do that for homework, like for practice?
Exactly.
Okay.
More confident. Yay!
Yay.
Okay.
I know what to do.
And you know how to do that.
Yes.
And then, well, B and C are easy of problem 23, once you get the first one correct.
Yeah.
Okay. Now, the most complicated moment of all times. How did you enjoy our chat?
I liked it. I understand what was going on, and I liked that there was a lot of like input from me, like a lot of like me figuring stuff out on my own.
That's the way I usually train people. It's useless if there is this Russian habit of passive education where
Yeah, just lecturing.
Yes, I lecture, you listen, and after 5 minutes it's like this. So yeah. Okay, glad to hear that. I will call it a day for now. I have my babies to be put to bed, and please feel free to do your homeworks and send them within today, so that you don't need to have to be really precise. I'm not picky. I'm really not picky. If the idea is there, that's enough.
Okay.
We can.
So do you want me to send you the what's it called? Do you want me to send you the free body diagrams as well?
Yes.
Okay, sounds good.
Just picture.
I'm gonna have access to this board, right?
Yes, it's always there. It's always there. Especially when we will create your own, then there's gonna be just your things there, because maybe I am lecturing another couple of pupils on this board, so it might be complicated for me to find where we were left at. Okay, great.
Okay.
That said, have a good afternoon.
Thank you. Have a good evening.
Well, it's night already, so I'm going to put my babies to sleep.
Okay. Bye-bye.
Bye-bye. Thank you.
To meet you.
My pleasure. Bom.